Increasing atmospheric carbon dioxide from the use of fossil fuels is leading to rising temperatures, loss of habitat, and loss of economic productivity. The recent Paris Agreement is an important commitment by 195 countries to substantially decrease CO2 emissions. But how are we going to do that when we are so dependent on fossil fuels in energy production, in industry, and in transport? Hi, I'm Peter Cook and I'm a geologist. Carbon capture and storage, or CCS, has the potential to achieve deep cuts in industrial CO2 emissions. Australia has been at the forefront of CCS since 1998. Demonstration of CCS has been underway in Australia for more than 10 years, and soon the Gorgon project in Western Australia will be the largest industrial CCS operation in the world. Research and development such as that undertaken here at the Peter Cook Centre, the University of Melbourne, is critically important to Australia as it progresses along the path to CCS deployment.
I'm Rolf Hayes and I'm the Director of the Peter Cook Centre for Carbon Capture and Storage Research here at the University of Melbourne. The Peter Cook Centre is a vibrant community of students and researchers working on two overarching objectives: to reduce the cost of the CO2 capture process and to develop the knowledge and the tools to ensure safe CO2 storage in the deep subsurface. There are three strengths we are particularly proud of. Firstly, we have world-class laboratories allowing us to be truly innovative in our research and to deliver high-impact research results. Secondly, we offer classroom and research training for our postgraduate students and professionals to train the next generation of engineers and scientists for the emerging CCS industry. And finally, we collaborate with a large number of research partners. One good example is our collaboration with the CO2CRC, a member-based, non-for-profit organization which develops and manages research activities at the CO2CRC Otway site in Western Victoria. This subsurface laboratory is exceptionally well characterized in terms of its geology, and it therefore offers an outstanding opportunity to test and demonstrate geological carbon storage in the deep subsurface.
I'm Catherine Mumford. Here in the Carbon Capture Lab, we test, develop and provide support for the commercialisation of advanced solvent absorption systems for the separation of carbon dioxide from a variety of industrial gas streams.
Hello, I'm Barry Hooper, CEO of EuChems. We've had a long association with the Peter Cook Centre and the University of Melbourne over many years. Over the last year we've been building new equipment alongside the existing capture facilities and showcasing our EuChems Mark III technology.
I'm Mandy Mann, a PhD candidate and member of Peter Cook Centre for CCS Research. In our research group, we mainly focus on the CO2 absorption and utilization. My project is to convert CO2 to some value-added chemicals, such as methanol and other alcohols. It is widely known that the input energy to produce methanol from CO2 is incredibly high. The novelty here is trying to find a pathway where CO2 can be utilized under less energy-expensive conditions. This new process would not only be a way to mitigate the greenhouse gas, but could also produce an alternative and economic feedstock.
I'm Jay Black, and I work in the Environmental Geochemistry Research Group. Injecting and storing CO2 in the deep subsurface very much depends on how easily a fluid or gas can flow through the rock's pore space. Many of the projects we work on explore ways of either enhancing the flow capacity to allow for higher CO2 injection rates or just the opposite, forming flow barriers to mitigate the risk of CO2 leakage. As an experimental geochemist, I conduct experiments using equipment that can replicate the pressure and temperature conditions found in the deep subsurface, so we can gain a better understanding of these processes.
I'm Stefan Mattei and leader of the Reservoir Engineering team of the Peter Cook Centre. We develop and apply software, improving workflows for performance prediction and simulation-based design of CO2 geostorage. As example, this screen shows a computer simulation of CO2 injection prepared as a contribution to a collaborative research project with Stanford and Cambridge University. This research was funded by BHP. This is a model of a gravel pit with a layered structure that is similar to that of storage targets buried in the subsurface. CO2 is injected on the left, migrating to the right, driven by the injection pressure. The ease with which fluid flows through rock is shown in grayscale. White is easy, black is hard. You can see that CO2 is channeled into central layers. Simultaneously, it rises because it is buoyant, but capillary forces prevent it from entering fine-grained layers. The resulting CO2 migration pattern is really counterintuitive, illustrating the strong influence of varying rock properties on plume shape and CO2 retention by the layer. Such intricate behavior is not captured by conventional simulation software. We try to overcome this dilemma by developing next-generation software and applying it to more physically realistic models of storage pilots, like Otway.
Carbon capture and storage is a key climate mitigation technology, which will enable industries and the economy to transition to a low-carbon world. Research and development here at the Peter Cook Centre, in collaboration with its Australian and international partners, has a major role in taking CCS forward.